what we're going to be doing today is we're actually going to be taking a look again at the Swift programming language, but specifically, we're going to be implementing something a bit more advanced than what we get into in the book. So if you take a look, this book teaches you all the fundamentals of Swift. It teaches you programming, it teaches you, iOS app development. And at the very end, we stop at around Sprite Kit. And so I teach you how to do like some relatively complex 2D graphics work. From there, though, there is still a lot of scope as to more stuff that you can do with the power of Swift and with the power of the frameworks that Apple gives you. And so today, we're going to be taking a look at a very specific framework called CoreML. CoreML is a framework that's built by Apple and available on all different Apple platforms. And the idea is to make it easy for developers to incorporate machine learning technology into their applications using the very powerful hardware that Apple gives you on their devices. Before we even get into that, what is machine learning? Well, what I'm going to do is show you just a really quick example of what machine learning, deep learning technology does. And again, this is going to be super interactive, so I do have the Twitch chat open. If you have any questions, feel free to put it there. And now let's go ahead and take a quick look at what deep learning technology is all about, why exactly we would need a framework like CoreML to run that technology on our phone, or on really any iDevice. And then let's go ahead and take a look at how we can implement some relatively complex, but I would say really fascinating technology made simple by CoreML. Specifically, these are called language models, but we'll get into that in just a moment. I'm going to open up a playground, or what's something called the Tensorflow Playground. And so Tensorflow Playground. But just really quickly, the reason that I've opened up this thing called the Tensorflow Playground, actually, if you've read the book, you know what a Swift Playground is. And essentially, a Swift Playground is where you can play around with different Swift tools and Swift code so you can figure out how your code works in real time. And the Tensorflow Playground is something similar, but for neural networks, which are a kind of machine learning algorithm. And if we were to take a look at the Tensorflow Playground here, what you're seeing on screen will make a lot more sense if I give you a bit of a description as to what exactly a neural network does. Well, the idea is that let's just say we have two different data sets, say X and Y, and we know that there's some sort of relationship between them. And so, if you have X, then it's plausible that you could predict Y based off of X. But we don't know how to do that mathematically. So let's just say I were to give you a picture of a dog or a cat. Let's call that X. And your Y would be, well, what is this? Is this a cat or is this a dog? And you can't really make a mathematical function to do that because as a human, we can't really mathematically describe how we recognize different things visually. That's not exactly easy for us to do. In fact, that's not really possible for us to do, or else it would have been done. But with a neural network, what we essentially do is we offload that task of building that mathematical function to the computer. And so now, instead of us having to, sit down and write the mathematical function that's able to go into X and figure out what Y should be. So for example, take an image and determine if it's a cat or a dog. Suddenly, the computer can do it for us now. And the TensorFlow Playground is a highly simplified version of similar technology that lets you sort of visualize how these neural networks work. And then once we visualize that, I'll go ahead and show you how we can port this over to iOS and actually use it on an iPhone. So let's go ahead and take a look at that. Now, on screen right now, within the TensorFlow Playground, one thing that I'm going to do before we even start, and I'll explain why we're doing this in a moment, is reduce the hidden layer count to just 1 and the neuron count to just 1 as well. So now you should just have 3 lines. These might be different colors for you, but you should have 3 different lines, 2 from this side of the screen to the middle, and then 1 from the middle over to the end. Now, essentially what's happening is on the left is your input to your neural network, which is essentially, again, your mathematical model, your machine learning model that's able to convert input to output. Now, what happens is the input that we're feeding in 2 different sort of inputs to the model. One of them is called X1. And essentially the idea is that if a certain point on the graph is more towards the left of the graph, like over here, for example, this dot over here, if it's more towards the left, then X1 for that point is going to be more negative. It's going to trend towards -1. Whereas if it's the opposite side, so for example, if say this dot over here is towards the right, it's going to trend to +1. So if I highlight x1, you should see that the background towards the right is blue, towards the left is orange. That means orange towards the left is -1. That's sort of where x1 activates as -1, and towards the right it activates as +1. In the middle, you can see that transition area where it sort of merges and bridges through a 0. In between, like when x is 0, x1 also is 0, and then negative and positive towards left and right. And then the second input that we feed to the network is just similar, except it's positive towards the top and negative towards the bottom. And so what that does is it sort of gives us information for both left, right, and up, down, but through two separate inputs to the machine learning model. Now what I'm also going to do is, just to sort of make this a bit easier, I'm going to switch the data that we use over here to the Gaussian data. This is an easier data set to work with, and I'll explain why in just a moment. Now this node over here, this node is actually very interesting because it's what's called an internal or a hidden node of a neural network. So what that means is that we don't know exactly what this neuron is calculating. What we do in order to calculate its value is we take our two inputs, we multiply them by these things called weights, and then we sum together those weighted inputs, and suddenly we've got the value for this neuron. Now, how exactly do we determine those weights? Well, that's the secret sauce behind machine learning models. That is what we use some complex mathematics to figure out, which luckily is mathematics that you don't need to care about because of the way that we're going to be training our models today. As a matter of fact, the goal for this neural network is to be able to make it so that behind all of the orange dots in this graph, there's an orange background, meaning so the network predicts that, at this location, the dot would be orange. And behind all the blue ones, we want a blue background. So the neural network is predicting that for these dots, they're more than likely blue. That's the goal. Currently, it's kind of flipped. So you can see we have an almost vaguely orange behind the blue and a vaguely blue behind the orange. But when we click the play button to start training the neural network, suddenly, as you can see, it pretty much instantly figures out the pattern that orange or dots on this side of the graph are usually orange, dots on this side of the graph are usually blue. Now, really quickly before we move on, I do want to say that the input that you feed in really does matter in terms of how your network is going to perform. And so, for example, let's just say I were to only feed in the left-right XY. Then, well, the neural network doesn't have enough data to draw a diagonal line. It can only really draw the line straight up-down, which in this case works. But if one of these dots was slightly more towards the left or slightly more towards the right, that wouldn't have worked well. Similarly, if we only feed in the up-down data and not the left-right data, then as you can see, it sort of misclassifies this one dot because it's almost an outlier. But then when we feed in both pieces of data, look at that, the network is able to use both and create a much better line in order to separate those two pieces of data. It doesn't seem like much, but when you scale this up from left, right, up, down to pixel values in an image, and when you scale from dots on a graph to labels of what's in the image, then you get really, really powerful results. Like when you actually open up your phone, for example, and when you talk to Siri, or when you open up your phone's photos and it tells you whose face is in whose photo. It's powered by very similar mathematics, machine learning tech. One more thing that I want to mention really quickly is that this data set in particular was really, really easy for the neural network to adapt to or to learn from. And that's because the data is what's known as, in mathematical terms, linearly separable. And so just a single straight line between these two data sets would split the two sections of data perfectly, a single straight line. But then there's oftentimes data sets where the data is not what's known as linearly separable. So for example, this data over here. It's impossible to draw a single straight line and perfectly separate all the data in this graph, because if you were to draw it diagonally, then, well, you have some blue on one side, some orange on the other side, and so on and so forth. Even horizontally or vertically, you can't do it. And so right now, if we were to use our simple two inputs, left, right, up, down, and a single neuron in the middle and click on play, we don't get very good results. The network is just kind of trying to fit to something, and better than nothing at least. But the reason for that is because we only have a single neuron in the middle, and single neurons are only capable of modeling linear relationships. And so what we need to do is we need to add more neurons so that it can capture more a sort of more rounded interpretation of the space. So let's just say we add another neuron. In theory, we should see two straight lines now. So approximately something like so. But it's still not particularly complex. So if we wanted to be able to draw more complex lines, then what we can do is add another layer of neurons. Now we've got two neurons in two layers, and all of these weights again are figured out automatically by the math. We click on play, and suddenly we're drawing much more complex lines. And so that is machine learning technology in action. Now, in this relatively simple example, we can go ahead and count the number of weights that we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So we have 10 weights that are helping us decide what the output for the model should be. But here's the issue. 10 weights is nothing. For this really simple example, 10 weights is more than enough, right? We do not need more than 10 weights. That would be overkill. I mean, I could easily go ahead and add another layer, maybe some more neurons, and it would be really good at the task. As a matter of fact, sometimes they're actually bad. As you can see right now, there are just too many weights, and the neural network is actually having a hard time because there are too many weights to contain all that information. So sometimes that's not a good thing. But then as we work with more complex data, sometimes it becomes necessary. Like this data set over here is way more complex. We've got like a circle of blue in the middle surrounded by a ring of orange. This requires a more complex architecture, but still these numbers of weights are nothing. And as a matter of fact, if you were to take a look at some of the larger models in the industry, we can get up to hundreds of millions, even billions, and the largest hundreds of billions of weights. That's a lot of weights. And so you need a lot of compute power in order to process all of those weights. As a matter of fact, I would say that pretty common nowadays, you've got models that go into the hundreds of megabytes worth of weights, which is again a lot of data to work with, a lot of compute that needs to be done to figure out what the machine learning model is trying to say. And that is why Apple built CoreML. Because as a programmer, you shouldn't have to worry about, how exactly am I going to take my weights and compute with them really efficiently and make it so I don't take up too much power, but at the same time, it's really fast for the user to work with. This is the kind of stuff that Apple engineers worry about so that you don't need to. Another really great advantage is that within the iPhone, you've got special chips, like for example, the GPU and the neural engine, which are little processors that are dedicated towards making it faster for you to do machine learning inference. So when you take a machine learning model just like this one or more complex and you export it to CoreML and then feed it into your iOS application, they're able to automatically use all of those chips and make it super, super fast. So now that we've talked a lot about CoreML, how about we actually take a look at it in action? First thing we're going to do is we're going to open up this website called Write with Transformer. Now, Write with Transformer is a website from a company called Hugging Face. It's a pretty incredible website and actually powered by some pretty incredible technology too. Essentially, what Write with Transformer does is it's an online demo of these things called transformers. Transformers are sort of like the state of the art when it comes to dealing with language with machine learning technology. Because, I mean, think about it. Language is really, really complex. You could have a sentence like, I shot an elephant in my pajamas. And what does that mean, right? As a human, maybe with some context, you could figure it out. But in order for you to understand what that sentence means, again, you need the context, right? It could mean that you're a photographer and you're taking a picture of an elephant while you're wearing pajamas. Or you could be hunting an elephant while the elephant is wearing your pajamas. As a matter of fact, one of the most creative interpretations that I've heard at a research conference that I was at actually was that you're wearing pajamas and there's little pictures of elephants on the pajamas and you're taking pictures of your pajamas with the elephants on them. And so there's all sorts of interpretations you could have. And so writing mathematical functions in order to actually figure out what exactly a sentence means is impractical. So we need machine learning or deep learning technology to help us do that automatically. And the Write with Transformer website helps us demo or take a look at or interact with that technology as well. I'll actually go ahead and sort of show you or tell you what a transformer is as we go ahead and try it out. So what I'm going to do is I'm specifically going to take a look at a model called GPT-2. It's from OpenAI. And I'm going to click on Start Writing. And I'm going to delete the text that's already in there. And let me show you what a transformer does, and at the same time I'll tell you what it is and how it works. So let's just say we were to take a simple sentence like, I'm currently demoing some really amazing technology, right? Now, what this transformer model is trained to do is it's trained to take all of the text that I wrote, so all of this text on the left, metaphorically. And it's supposed to take that and predict what the next word would be in this sentence. Then, after that, after it predicts the next word, that's fed back into itself. And then it predicts the next word. And then that's fed back into itself and it predicts the next word, and so on and so forth. This is called an autoregressive language model. All right, so let's just say I go ahead and click Tab at this point. What's going to happen is the neural network is going to take a look at the text that I've already written. It's going to predict the next words word by word. So as you can see, it says the top two sort of next predictions are, I'm currently demoing some really amazing technology on the demo floor, so stay tuned for more, and I'm really excited by what I've got. So I can just select whatever I want to, and then I can keep hitting Tab, and it's going to keep going ahead and printing more and more text. And as you can tell, this is pretty good text. I mean, it's saying, I'm also very excited to bring my own experiences of using the system to the community. That makes so much sense in context. Of course, as we continue to generate text, it might degenerate a little bit, like it might not continue to be as high quality as we expect it to be. Again, this is a neural network. I mean, we've got to cut it some slack. It's a deep learning system. But again, it is writing really good text for a computer standard. Really quickly, I'm going to go ahead and answer that next question. What is a transformer? So if you think about natural language, you might think of it as what's known as a time series of data. So like, for example, the word amazing. The meaning of that word depends on and is changed by all of the words that came before it. And in some cases, even the words that come after it. But for now, for the sake of simplicity, let's assume that it's just the words before it. Now, in order to really understand what amazing means, you first need to understand all of the words before it and what they mean in context with each other. So traditionally, what we would do in the world of deep learning is we'd use these things called recurrent neural networks to understand this kind of data. And recurrent neural networks basically look at the word I'm, and then they create this little internal mathematical state of the word I'm. And then they look at the word currently and the previous state, and they combine them, and they're like, okay, this is my new state. Then they look at the word demoing and the previous state and combine them, and so on and so forth. And it keeps combining that previous state with new mathematical representations of each word. And they sort of go along the whole sentence word by word like that. But that is incredibly inefficient because you're looking at it word by word, right? Like, for example, when you're processing the word really, you're not allowed to start processing the word technology until you've also processed amazing. And so computationally, it's really inefficient. The CPU is capable of processing hundreds of words at the same time, but because the recurrent neural network is only looking one word at a time, well, you can't really use your CPU to its fullest potential, and it takes a long time to compute that sequence. And so that's why I believe researchers at Google wrote a paper called Attention is All You Need, which is where they introduced the transformer architecture of neural network, which, again, it's a neural network kind of like what we saw on the playground, but way more complex. It's got all different kinds of operations within it. But at the end of the day, it mostly just boils down to matrix multiplications. And the way it works is by essentially looking at the entire sentence or the entire sequence at once. And what it's doing is it's combining every word's representation with every other word's representation. That might seem a little bit more inefficient. Like, if you could just look at it word by word, why would you want to do, every word against every other word? Doesn't that doesn't that make it more inefficient? But no, actually it doesn't, because today's computers are capable of processing all of that data at the same time. So transformer technology is pretty incredible, and it is sort of the state of the art when it comes to understanding language with the power of computers. Also, another question from Powerman, not a question, but he's saying, is this something similar to what Google is using in their Gmail app now, where it auto-completes your sentences? You're absolutely right, it totally is. It is incredibly similar to that technology. As a matter of fact, I would not be surprised if they are already using transformers under the hood in order to do that for their Google Smart Compose feature. And so that is... as a matter of fact, I'm pretty sure they do. That's probably why they invented that technology. That's why their research teams were working on it in the first place. So yes, it is incredibly similar technology. Now what we're going to do is we're actually going to go ahead and implement this transformer model on an iOS app. And we're actually going to be able to generate similar text in iOS. First thing I think we should do is go ahead and prepare a simple Swift application that will act as the almost template that we're going to use and sort of integrate our technology into. So I'm going to go ahead and create a new Xcode project. I'm currently on the macOS Big Sur beta, but if you're not, no worries. These steps, because of the sort of frameworks that we're working with, should be pretty much the same. The only thing that might look slightly different is your user interface for Xcode. But apart from that, most of what we're doing today should be the exact same. So of course we're going to be building an iOS application. So we're going to click on iOS app. I'm going to call this, let's call this auto typer. All right, let's call that. And we're going to be using Swift UI as our user interface framework today. So I'm going to go ahead and put this onto my desktop, and we're going to get started here. Now, the way that Xcode works nowadays is, instead of giving you a storyboard and putting the different UI elements on there, we're going to be coding the user interface with actual Swift code, which is way easier when it comes to more complex user interfaces, and you'll be able to take a look at some of that today as well. So let's think of a good UI for this. I'm thinking we put a little text field on the top of the screen, and the text field then has a button under it. When you click on the button, it goes ahead and uses the GPT-2 language model to go ahead and compute the next words in the sentence. And there's another text field at the bottom which fills out what the model sort of wants to extend your sentence as. So for that, I guess we start off with a text field. So let's see, yes, SwiftUI does have a text field element. We can give it a title and some text, which I will go ahead and show a preview of the view as well in a moment once we do that. But then again, a text field is only a single line. So let's go ahead and do a text view, which unfortunately has not yet been bridged over to SwiftUI. So we are going to be using a text field. Let's just give it a title as, let's just say we want to feed in some seed text. All right, and the text that we put into the text field will be stored in a variable called seed. So we're going to create a state variable called seed. It's going to be of type string. This is really interesting because in SwiftUI, all you need to do is create a string and sort of tell Swift that it's a state variable, meaning that it's interacting with the user interface, and suddenly you can pass that seed over to the text field. And instead of having to store the text field as a variable, you only store the text within it as a variable within your view. So now we go ahead and let's just say we give it a default value of a blank string, build it. It should build successfully, no syntax errors, and show a preview. All right, wait for the preview to show up. Right as it does, though, we'll be able to see that in the middle we have of our little view. In the middle, we have a text field where the placeholder is called seed text, and then right as we enter some text in there, we should be able to take a look at the text. All right, it says failed to build content view. Let's see why that is. Failed to build auto view because it can't import auto typer. Well, let's try just cleaning the Xcode project, and maybe now we'll be able to preview properly. Ooh, still does not want to preview. Well, let's just go ahead and run this on the simulator. And we will more than likely just be able to take a look at the interface within the iOS simulator. Again, in the book, I do show you, how you can actually go ahead and use different ways of running your application, whether that be through the iOS simulator or on an actual iOS device. So if I go ahead and extend the simulator view a little bit so we can actually see it, there we go. We see it's currently booting up. Give that just a moment to go through. And then right as it boots up, I will show you the user interface. Until then, let's go ahead and continue coding what this UI needs to look like. So under the text field, as I mentioned, we're going to have a button that right as you click it, it goes ahead and fills out the rest of your text based off of what the transformer thinks it should go ahead and fill out. So I'm going to go ahead and embed this in something called a vertical stack, which will enable me to stack multiple UI elements vertically. And then right under that, I'll put a button. With the button, we should just put in some text. So let's just say we put a title. Let's call it Generate with GPT-2. Oh, there we go. Our iOS simulator is launched. Give it a moment to actually start the application. Sometimes that takes a minute because of how the simulators work. But until then, let's just go ahead and continue to code. So when you actually click on the button, what I'm thinking we should do is call a function called generate on the actual view itself. So we're going to create a new function called generate, and this is where we can handle the generation of text with GPT-2, which is something that we still need to implement. All right, so as you can see in our simulator, we do have the seed text field, which is currently stuck towards the left. And in order to solve that problem, we can just put some padding on the V stack, which will give us a little bit of space towards the left and the right and top and bottom. So we've got the text field, we've got the button, and right after the button, we're going to put another label. So we're actually in SwiftUI, labels are just called text. And the text that we're going to be showing, let's just call it generation. And so we're going to create a new state variable called generation. And this is going to store what the neural network actually generates, which we will go ahead and show with this text. All right, let's just go ahead and see. All right, so what we need to do is actually put this within a string because, SwiftUI requires you to pass a string to text. Let's just make sure that actually builds. No, it doesn't. Let's see what it's telling us. No exact matches in call to instance method append interpolation. Well, simple way to fix that. We don't need this to be a binding. We just need this to be a regular string because text isn't going to modify this. And so we don't need to do any real interpolation. So now let's just go ahead and quickly take a look at what our UI looks like. So I'm going to rerun this in the simulator, and then we'll go ahead and implement the actual transformer technology. All right, as you can see, launched pretty quickly this time. We've got our little text field where we can enter seed text. So I can be like, this is a simple sentence. And then we click on generate with GPT. And in theory, once we implement the actual transformer library, then we should see the label populate over here with the text from the transformer. So now let's go ahead and do that. And in order to do this, we are going to need, two things. We're going to need to install Python, of course, and on Mac that comes by default. Nowadays, luckily with Python 3, since Python 2 is nearing end of life. Or actually, I believe it has already hit end of life. But along with that, you're going to need to install two separate libraries. So if I go ahead and open up my terminal over here, you're going to need to install CoreML tools is one. So the reason you need CoreML tools is because that's a library by Apple that enables you to actually deal with transforming your neural network models into CoreML format. And then apart from CoreML tools, you're also going to need Torch, which is actually PyTorch, which is a neural network library in Python, as well as Torch Vision. So Torch Vision is just another package that comes along with PyTorch and has a bunch of utilities to help you implement deep learning algorithms more simply. So you're going to be using CoreML tools, Torch, Torch Vision, as well as this thing called transformers. So this is, again, a package by Hugging Face. Transformers enables you to deal with the sort of cutting-edge language models really, really easily. So instead of having to implement all of that yourself, you can just use the implementations that have already been made for you by the experts over at Hugging Face. So go ahead and install all of these. I've already installed these because it takes a little bit to install, so I don't want to have you watch paint dry, so I've already done that for you. And once you go ahead and do that, then you're also going to want to git clone a couple of repositories. One of them is called Swift CoreML Transformers, and it's also by Hugging Face. Once you go ahead, what you're going to want to do is run a git clone of this repository, and then after you've done the git clone of that repo, then go into the repo. So we can just cd into it, and then within that folder, you're going to see a couple of different folders. One of them is called model generation, and so you want to go into model generation, and if you take a look, there's already a file called gpt2.py. Now, there is a bit of a catch here, and so I will explain that in a moment. I see a question from Powerman2824. Could I build this environment on a Linux virtual machine? Absolutely, you can. This part of the experiment, which is the actual creation of the model itself, the CoreML model, yes, you can do that on Linux. But then when you actually want to develop the iOS application and deploy to an iPhone, that is when Apple's ecosystem comes in, and that's when you have to use a Mac. You cannot use a Linux machine for that, unfortunately. At least, not yet, and it doesn't seem like Apple's going to want to let us do that either for some time. But regardless, you can do this section, which is the sort of Python end of things, on a Linux virtual machine. Oh, okay. If you're on a Windows machine, well, again, you cannot, unfortunately, actually implement the iOS tools. So you're not going to be able to code the iOS application itself. But the part of the environment that's responsible for converting the Python model to a CoreML model that iOS can understand, that you can do on a Linux VM on your Linux machine. You could more than likely, if you're on Windows 10, use the Windows subsystem for Linux. That's super high performance. That's a great way to do it. Otherwise, if you actually have a Linux VM, then you can do that too. So both should work. So within this file of code that you've gotten from the GitHub repo, what you're going to see is there's actually quite a bit of code here that deals with transforming this model into something that CoreML is happy with. As you can see, some of the code is a little bit dirty. Comment from one of the code creators, I hate this. So there's unfortunately quite a few different workarounds you've got to do in order for this to work, but at the end of the day, it gives us the result that we want, and that's really all that matters. So if you take a look at what's going behind the scenes here, there is one small modification that you're going to want to make. By default, when you clone the repository, it's using a slightly older version of Transformers. And so this is not going to be here. This line over here is going to be slightly different. And so what you want to do is where it says for Transformers import, you want to modify that to from Transformers .modeling GP2 import. So make that small modification, and then you should be good to go. So once you've done that, you should be good to go ahead and actually run this script. So I'm going to go ahead and invoke that script. Again, I'm running this on Mac. You could quite as easily run this on Linux as well, as long as you've got all the different dependencies installed. And then as you run this, what's going to happen is first it's going to go ahead and download the actual models themselves. So the raw PyTorch versions. That's around 0.5 GB. So again, these are really big models. So I've already gone ahead and done that for you. And also, really quickly, I will, just to sort of let you know, towards the end of the stream, I will be showing you some more interesting examples of what you can do with CoreML that's pretty unique, that you can't do with a lot of other libraries, and we will take a look at that in a moment. But for now, as you can see, I go ahead and run the script. It converts the model from PyTorch to CoreML format. It goes through all of these different layers, all the different 11 layers of the model automatically. And then if I go back a directory, and then I go into the resources directory, you can actually see that just now at 12:37, which you can confirm the time is 12:37, it wrote a file called gpt26412.ml model. What this means is that we took a small version of GPT-2 essentially, and converted that to CoreML because, I mean, we don't want to deal with the really large versions of GPT-2 at the moment. If we were to take a look at the actual size, we see this is around 622 megabytes. And that's the small model. All right. So these models can get really, really big. This is more than half a gigabyte that we're going to be putting on an iPhone. So we'll take a look at that. And then once we handle this, then I'll also show you how you can make these sizes smaller. So we'll talk about that in just a moment. For now, though, don't worry about the size. That's just how it is, and we will deal with it momentarily. So what you're going to want to do first, though, is open up this resources directory. And so this is where Linux, unfortunately, will stop working because we got to open up Xcode again. So open up Xcode, open up your little file browser on the left here, and you're going to want to take the ML model file that we just made and drag that into your Xcode project. Give that a moment. Oh, do I need to do this the old-fashioned way? Ooh, okay, so drag it into mission control, and then there we go. So I'm going to drag the ML model into here, make sure copy items is checked, and then click on finish. Now what's going to happen is Xcode is going to slowly but surely take your ginormous model and put it into your Xcode project. I know it looks like nothing is happening, but that's just because Apple, for some reason, doesn't give us a progress bar. Xcode is currently working on copying in the CoreML model. The reason this takes a moment is because you're not just copying. Xcode is also now looking at the CoreML model, and it's automatically generating a bunch of Swift code that deals with actually, providing input to the model and taking output from the model, and it's doing a bunch of boilerplate code generation as well. So give that a moment. That's going to take a little bit to copy in. There's not much that we can do to make this faster. Now, another thing that you should keep in mind, oh, there we go, it just came in. But yeah, another thing that you should keep in mind is that this is Big Sur, which I believe after macOS Mojave, Apple started to use Apple file system. And because of the spec of that file system, copying files is super fast. So it wasn't the actual copying that took that long. It was Xcode just processing this huge model that took a couple of seconds. So we got this model in Xcode now, and as you can see, we can go ahead and see what sort of operations are being run within this model. So we've got 96 different transpose operations. We've got 49 and 49 of the scale and inner product operations. We've got rank preserving reshape, all these different operations within the actual model itself. And Xcode gives us this nice graphical way of viewing what the individual operations are that are being done within the model. This is what Xcode allows us to see. We can also take a look at the predictions as to what the input and output of the model actually is. And the different utilities. So for example, let's just say you want to encrypt this model. And so what that would let you do is make it so that people that have your application can't just take their model out of the application, use it in their own applications. And so Apple will actually help you encrypt your model as well, so that you can keep your own intellectual property your own, even when you ship it on an iOS device. As well as what's called a model archive, which enables you to put a CoreML model into the cloud so you don't actually need to have it on the device. So quite a few different interesting features, but we're not using any of them today because today we're focused on getting a really good text generator on an iPhone. That's our goal. We've got the actual model in the code now, but now we need some sort of code to deal with the model itself. And to actually feed it the input that it expects and take the output and decipher it and tell our code what it means. Really quickly, I'm going to take a bit of a detour, a bit of a tangent, and go back over to the Write with Transformer website. Really quickly, just so you know, before I told you that these sorts of natural language pieces of data could be thought of as time series, right? So you could use recurrent neural networks to look at I'm and then look at currently and so on and so forth, and it would be able to understand the text. The advantage of that is that the recurrent neural network is able to model the time or the sort of order of the words themselves. So for example, if you take a look at I'm and then currently and then demoing, when you mix in the state of demoing with the state of I'm currently, you're able to sort of automatically learn mathematically that sense of order. But then with a transformer, since every word is interacting with every other word, transformers inherently don't really have that sort of sense of order. There's no way for a transformer model to determine if the word technology is at the end of the sentence or the beginning. The mathematics are the exact same regardless. And that's an issue because in natural language, order means a lot. And so what happens is when you feed in your input, the way the transformer models for language models work is instead of just feeding in technology or just feeding in amazing, you actually sum the mathematical representation for the word amazing with the mathematical representation for the position of that word in the sentence. So if, for example, you have the word I'm, because it's in the beginning, you're going to sum the mathematical representation for I'm with its position and currently and so on, so that you're essentially shifting every input vector by a certain amount based off of where it is in the sentence, giving the transformer a sense of order. And that's why when you take a look at the predictions over here in the CoreML model, you see there are actually two inputs. One for the input IDs, which is, what word were we fed in, but also another input for the position IDs, which is going to tell you at what position was I fed this specific piece of text. So that's why we have two different inputs. So now we've got our CoreML model in the application. Now we've got to write the code to deal with it. Luckily, we are using the transformers library, and so a lot of this is actually already done for us. So if we actually go ahead and take a look at this, all I need to do now is go ahead and take from the sources directory in the repository that I've already cloned, and take these three GPT-2 files and drag them into my Xcode project as well. So just like that, drag them into my Xcode project. Go into mission control if macOS will let me, and then drag in my files. All right, there we go. And then I can take a look at these code files. They're pretty simple. It's just implementing the sort of prediction logic for GPT-2. There are three more files that you're going to need. You're going to need utils, ML multi-array plus utils, and math. So go ahead and take these three files as well and drag them into your Xcode project. Just like so. All right. So now if I go ahead and clean, or let's not even clean, let's just build. If I go ahead and build the project, you should see that we get no errors, and it looks like it is all working. Oh, we get one error. What is that error? Okay, it's because it cannot find the model name in this scope, but that's completely fine. We named our model something slightly different, so I'm going to go ahead and copy the name of the model file and then go back into this file and change that name. All the dashes are replaced with underscores. So replace the dashes with underscores, and then we've got successfully compiling code. All right. And as you can see, we even get our simulator running that code too. Okay. So now that we've got our code running, we've got to actually go ahead and call GPT-2. The way we're going to do this is by calling the code that was very nicely written for us by the folks over at Hugging Face. Now we're going to go ahead and instantiate a new GPT-2 instance. Let's just call this GPT. And then we're going to call a function from within it. Let's see what that function is called. If Xcode's not going to want to predict or do code completion for me, I guess I'm going to have to do it. So we're going to call something called the generate function, and it's going to take some text. It's going to take the number of tokens that we want it to generate, and then the callback. So what I'm going to do is GPT-2.generate, and what are the parameter names? Text and callback. So I'm going to pass it some text, and that's going to be the seed. And in the callback, we're just going to take some text, and we're going to do self.generation equals text. Now I'll explain the logic a little bit, and then I'll go ahead and explain why this works and some other slight modifications that we need to actually get this to work. So basically what we're doing is we're creating a new instance of the GPT-2 model within this function. And then what we're doing is we're telling it to generate some text, and we're giving it the seed text to base its generation off of. Then we're giving it a callback function, which is a function that we pass to the function, which is then called every single time another word is generated. So instead of just generating 10 sort of words at a time and then just printing out all 10, it'll actually show you as it generates in real time, word by word. So every time it passes you the text, we go ahead and put that text into the generation string, which is shown on screen. Now, one thing is that this may be, no, actually, never mind. I thought that this would execute in a background thread. Luckily, that doesn't happen, and so we do not need to do any dispatch queue magic. So now, watch this. In theory, right, as long as we didn't hit any errors, I should be able to just go in here and type in maybe something along the lines of, I love deep learning technology, and now, generate with GPT, and let's see if it does anything. Ooh, we get a bit of an exception. What is this exception? It cannot find 2 files that it needs. We forgot to drag in 2 of these files. Well, let's go ahead and do that now. So I'm going to go ahead and stop the application. I'm going to go over to the repo that we copied, go into resources, and we're going to get GPT-2 merges and also the vocab.txt, or sorry, GPT-2 vocab and GPT-2 merges, TXT and JSON. We're going to go ahead and drag those into the Xcode project. So I'm going to take this, put that into the Xcode project, like so. So what this does is it gives our application information about how exactly the machine learning model expects its input to be structured. So I'll go ahead and run the code once more. Let's take a look at the simulator. I love deep learning technology and generate with GPT. As we can see, it's working hard. We can actually take a look at what Xcode tells us, and it looks like it's generating, but it's not updating the text in real time. So we'll fix that in a moment. But for now, just take a look at the fact that there we go. So the network generates, I love learning of, oh, that's actually pretty exceptional. So I said, I love deep learning technology, and it generated, and I love learning about it, which is right. I love learning about deep learning technology, and I hope you do too. But that was the neural network actually generating text through CoreML. I think that was pretty incredible. But the only sort of limitation now is that we do not see the text updating in real time. And the reason for that is because this sort of changing of the text is happening on the same thread as the generation of the text. And that takes so much compute power that we don't end up getting the time to change the text on screen. So what I can do is actually call something called dispatch queue and go into the global queue and asynchronously run this code. And what's really interesting is that iOS makes it so easy for me to just say, I want this code to run in the background. And just like that, I've got code running in the background. And when I want to run some code on the main thread so I can update the UI, it's, again, just like one extra line of code, and suddenly I can do that. So I love deep learning technology. Let it generate. I believe we should see it updating in real time now. There we go. So it says, and I'm excited to see how it can, and then that's where the generation ends because it's only supposed to do 10 tokens. But that is incredible. We already have a machine learning model that can generate text, and that took us less than 30 minutes to do. The fact that modern technology and modern infrastructure like the Transformers library and PyTorch and CoreML and Onyx, all of these tools are working together in the perfect way to allow us to implement this cutting edge technology in under 30 minutes.